Hello GATE aspirants, welcome to part 9 of GATE solid state physics series. Question number 7. For the given unit cells of a two-dimensional square lattice, which option lists all the primitive cells? So for primitive cell, condition is this n effective has to be equal to 1. So we can calculate it for all these cases. For first one, it is 1 atom is shared by 4, so it will be 1 by 4 into 4, so that is equal to 1. So 1 is primitive. For second case also, it is shared by 4, so it will be primitive. It has only 1, 4, 5. And in case of 5, it will be 1 by 4 into 4 plus 1 by 2 into 2, that is equal to 2. So this one is not primitive. So option C is correct. 1, 2, 3, 4 are primitive cells. Next question. At low temperatures T, the specific heat of common metals is described by, so for metals, the formula is C is equal to alpha T plus beta T cube. So option A is correct. Next question. The high temperature magnetic susceptibility of solids having ions with magnetic moments can be described by chi is proportional to 1 upon T plus theta, where T is absolute temperature and theta is constant. The three behaviors, that is paramagnetic, ferromagnetic and antiferromagnetic, are described by. Now for paramagnetic material, chi is equal to 1 by T. So that gives us 1 by chi. So that will be chi is equal to 1 by T. So this theta for paramagnetic, it will be 0. So here theta is equal to 0. Next, for ferromagnetic material, chi is equal to 1 upon T minus Tc. So from here we can see that this theta is going to be positive then. Okay. Now for the next part, if it is antiferro, then in that case chi is equal to 1 upon T plus Tc. So these are the formulas for it, for paramagnetic, ferromagnetic and antiferromagnetic. So here this is negative, so theta is less than 0. Here it is positive, so theta is greater than 0. So option C is correct. Next question. If X is the dimensionality of free electron gas, the energy E dependence of density of states is given by. So for 1D, we know density of states is proportional to e raised to minus half. For 2D, density of states is proportional to e raised to 0. And for 3-dimensional, density of states is proportional to e raised to half. So if we have n-dimensional system, then for that we can write this as it is proportional to d by 2 minus 1, where d is dimensionality. So if I put 1 here, so 1 half minus 1 is minus half. If I put 2 here, 2 by 2 minus 1 is 0, and 3 by 2 minus 1 is half. So this is the formula, general formula. So value of y here is 1. So answer is 1. Answer range is 1 to 1. Next question. The energy dispersion for electrons in one-dimensional lattice with lattice parameter A is given by this equation. The effective mass of the electron near the bottom of band is. So this E is given to us. Let us find its derivative with respect to K. So dE by dK is equal to, E naught is constant, so this will be half W. Derivative of cos is minus of sine, so sine Ka, minus and minus will cancel out. Take double derivative, d2E by dk square, that will be equal to half omega into, we have A as well, we are taking with respect to K, so into A. So this will be A into A square into cos Ka. Now at the bottom of conduction band, we have K is equal to 0. So d2e by dk square at k is equal to 0, that will be equal to, if I put k is equal to 0 here, then this will be half omega, half w a square. And effective mass m star is equal to h cut square upon d2e by dk square. And that will be equal to then 2h cut square upon omega a square. So option A is correct. Next question. Amongst electrical resistivity, thermal conductivity, specific heat, Young's modulus and magnetic susceptibility, which qualities show a sharp change at superconducting transition temperature? So at superconducting transition temperature, electrical resistivity changes, then from here specific heat capacity changes and magnetic susceptibility changes. So option B is correct. So this question is based on pure theory. Option B. Then question number 38. A p-doped semiconductor slab carries a current I is equal to 100 milliampere. In magnetic field, B is equal to 0.2 Tesla as shown. One measures Vy is equal to 0.25 millivolt and Vx is equal to 2 millivolt. The mobility of the holes in the semiconductor is. So this is the question. Here magnetic field is in downward direction. So this is the direction of B bar. In this direction we have current, and in this direction we will have Hall voltage. So now Hall voltage is equal to, we will use formula for Hall voltage here. The question is to calculate mobility. So let us do that. Now mobility is equal to what? Mobility is sigma into RH, where RH is Hall coefficient. Also we have VH is equal to I into B upon, here we have T into NE, where this 1 upon NE part is RH. So this is Hall voltage. Now here let us write this in terms of these parameters that are given in the question. Hall voltage is in horizontal direction. So VH will be Vy. Then current is given IB. And this 1 upon NE can be written as RH upon T. So I can write, using these two equations, I can write mu is equal to, from here I will get RH, right? So that will be Vy by T upon IB. So let us substitute it. So mu is equal to Vy into T upon IB into, we have conductivity sigma. But sigma is equal to 1 upon resistivity. So that will be Ra by L. But R is equal to then voltage upon current. So voltage is in x direction. So Vx upon I. And then we will have A upon L here. So let us substitute this in this equation. So we will have mu is equal to Vy T upon IB into sigma is I into L upon Vx into A. So this I will cancel out and we will get mu is equal to T into Vy into L upon B Vx into A. So mu is equal to, T is this thickness, it is 10 raised to minus 3. Vy is 0.25, but it is in millivolt. So 0.25 into 10 to the power minus 3. Then length is, this length is given 10 millimeter. That is 10 into 10 to the power minus 3 upon B 0.2 Tesla into Vx horizontal. That is 2 into 10 to the power minus 3, 2 millivolt. And area is this portion, T into V. So T is 1 millimeter, so 10 raised to minus 3. And this portion width is 4 into 10 raised to minus 3. So this 10 raised to minus 3 will cancel out, and finally we will get mu is equal to 1.56 meter square per volt per second. And the answer range for this question is 1.55 to 1.58. So these were all the questions from solid state part from GATE 2018 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.